All right, we're good to go. So where were we last time? Anybody remember? Somebody wanted to prove something like this. So let F be convex and domain of F is all of Rn. We want to prove that f of x can be written as supremum over g of x such that g is affine and g of z less than f of z log z. What does this really mean? We have not yet proved it, but supposing it was true, what does this actually mean? G affine means that's clear. Just some A transpose X plus B. All functions which are essentially from below, they're approximating f of z. That's what it means. G of z is less than or equal to f of z for all z. You're trying to look at the soup of those functions. So for each x, something like this, it need not be a single g which will work for all x. Okay, it could be that depending on x, the one which gets to you to the equality might be a different function. So it's not necessarily a single g. But among the class of all g's which satisfy this, for each x, the supremum is actually equal to that. So the simplest f of x is, let's say, the quadratic function. What does it tell you? That you start drawing these and look at the largest. So from below, you start going upwards. You have to make sure that you never cross f of z. So for each point, this is my point x. What did it tell me? That f of x, if I am going from below, making sure that this is true, the point at which I'll hit the soup is exactly equal to f of x. So there exists some g for which this is true among the class of all g's. So is there anything? Why is it useful? Such a characterization. Is it surprising, first of all?
Surprising again, like we already proved that it's the convex set is the closed convex set is the intersection of the half spaces in it. But
Correct. So now, what connection actually you can make between the two? There's an obvious choice to make that connection. There we were talking about convex sets, now we're talking about convex functions. If your analogy is correct, that convex set is nothing but the intersection of all the half spaces that contain it, what is the corresponding connection over here? Which tells you that, okay, this should hold for convex functions as well. So what is convex for a convex function? There's one element, I don't want to use element. What's the correct term for that? One quantity which goes from a convex function to a convex set. And we know something for sets. And for a convex function, its epigraph is convex. So that tells you that if you can do something like this, it better be via the root of epigraph. Because for epigraph, I know that I can take the intersection of all half spaces, and that essentially is going to give me the epigraph. Okay, so we want to prove the equality. Which direction is easy? So we're going to show less than equal to and then greater than equal to. So which direction do you, but just by the definition, one direction is easy. So GZ by definition is below f of z. So which of the two sides are less than or greater than equal to without having to worry about?
F of x is greater than equals
Just by definition. Because of this. So one direction is easy. But here again, the domain, go back and think why domain f needs to be R of R. This is actually an exercise in the book. If this is not the case, you'll have to be slightly careful. Something else happens. So think about that. Is in fact greater than of g of x. G is affine and gz is less than fz. So that's easy. Now, how do we proceed further? Maybe this picture will help you. Tell me the idea and then we'll go. Now I want to show that either less than equal to or a g which is achieving that. Either of them is fine. And you can think of this as your epigraph. So what have we developed so far for an epigraph which will help us? So we're looking at this point x, right? So x comma f of x is your epigraph really. On the boundary, it's x comma f of x. Everything above is t greater than f of x. Okay, so this is my boundary point. What do we know? Given that epi is convex, that there is a okay. So let's call this the separating hyperplane. A comma. So there exists a separating hyperplane for point x comma f of x. So what can I use, or how can I use that? So for any point inside, what does this hyperplane tell me? All the points are on one side. That's the important one. Is that okay? That's what it means, the separating hyperplane. So the whole set is on one side of this hyperplane. So what do I get? For any remember, my point at which I'm drawing this separating hyperplane is x comma f of x. So why is this true? That's all. So just by the point x comma, by the separating hyperplane a comma b at point x comma f of x, I directly get this. Now what do I need to produce to claim what I'm trying to claim? So this just directly follows from epigraph and the separating hyperplane. What do I need? I need to prove this. You already proved greater than equal to.
And to be reverse direction, it's then it's the entire contradiction that you that Convex is not.
We're actually going via the construction method. Because what have we done? We looked at the epigraph, we looked at its separating hyperplane. So you got as inequality. Now there is no more contradiction. Now it's actually forward. We're trying to construct something. So essentially we're trying to construct a g of z such that g of z is greater than or equal to f of z. So what does this mean? What properties does z comma t satisfy given that they belong to a p of f? T is greater than f of z, right? T is greater than or equal to f of z, let's say plus ms, or s greater than or equal to 0. Okay. Now what can I do? Suppose I write equality here. What does the equation tell me if I were to expand this? It tells me A transpose x minus z plus b times f of x minus f of z and minus s is the equal. I'm just substituting for t equal to f of z plus s. Now this holds for all s greater than or equal to 0. So what can you say about b? Can b be 0? This is true for all s greater than 0. Then can b be equal to 0? So suppose b is 0. What will this imply? What implication will we get from this? That A transpose x minus z is less than or equal to 0 for all z. What does that mean? That A is identically 0. But if B is 0, A is 0, what kind of hyperplane did you start with? The whole point was it was a non-trivial hyperplane. So this implies that B cannot be 0. Non-trivial. Okay, so what we have established is B is not equal to 0. Now what can we say? Given that B is not equal to 0. And why do we care about B being equal to 0, not equal to 0? Because I can divide, really. So now what is the special point at which I can use that equation and the fact that B is not equal to 0? So this holds for all s greater than or equal to 0. So can you use that for a special s and the fact that B is not equal to 0 to write a new equation which will give us something? See, what am I producing? I'm trying to produce a family of functions g such that gz is less than or equal to fz, but there is a point at which x such that g of x is equal to f of x. Keep that in mind. Everything is on the board. So all you have to do is to produce a g of z, which has this property that g of z is less than or equal to f of z. And g of x is equal to f of x. That's all. And everything is on the board, I claim, to do that. So what special value of s you want to evaluate this equation at? That's all you really need to do. Is the goal clear? What we are asking? We are asking from this equation. Let's call this hash 1 from 1. Define or manufacture, whatever. Let's call it manufacture g of z such that g of z is less than or equal to f of z. A requirement for me such that g of x is equal to f of x. That's it. I want this. This is true for all possible values of s, so I can evaluate at any value of s. And I have the fact that b is not equal to 0. That is all you need to do this. The goal should be clear. You get it or not, whatever we have written down, the goal should be really clear. We want g of z to be less than or equal to f of z by definition. Otherwise, the task will be incomplete. And at the same time, I want g of x to be equal to f of x. And that is why for each x, a g will be different. All you need to do is to just manipulate that equation. It's actually staring in your face. What would be the obvious guess for satisfying the first property? What will be your definition of g of z? What quantity is less than or equal to f of z from equation number 1? It's as simple as that. What is g of z? I have not defined g of z for you. Look at it, equation number 1. Just by pure algebra, what quantity is less than or equal to f of z? Correct, is less than or equal to b times f of z. Okay. Now you have the freedom of choosing s and the fact that b is not equal to 0. Now can you say more than what you just said?
Choose b equal to 1.
Okay. You can't choose b equal to 1 necessarily. S you can choose whatever you like. So what's the obvious choice for s? 1 by b. Why not 0? Is it clear what we're after? Okay, tell me what are we after?
We have the choice for S.
Yes.
We are trying to show that we can have GZ to be
But what is gz? I have to define gz as to be something. So what's the obvious thing to define gz as?
the left hand side of the manipulating.
Yes, so why are you not doing it? Why are you hesitating to do it? Don't hesitate.
I am just thinking,
Yeah.
if Z is fixed, are we fixing Z and then proceeding here?
What is fixed? You tell me what, like this question I don't understand. So you tell me what.
In that equation,
Yes.
X and Z can vary, right? Or
What is x comma f of x? One point of the epigraph at which I am looking at the separating hyperplane. What is z comma t?
T is anything for 1 point in the epigraph.
So now answer it for yourself what your question is.
S equal to 0 and then we get that and B equal B can't be so.
What are we trying to produce? Read this carefully. What are we trying to do? If this is clear, there should be no doubt what we are trying.
Then A transpose.
So tell me what is the where is the doubt coming from? What is the statement?
Here it is, like, I have understood this, that part.
Okay, then why is the question coming up is the question. If you understood this, there should be no reason to doubt that. For each x, I'm doing this exercise. So where is the question?
We will get A transpose by B time.
Let me finish it. This is the point at which I'm drawing my hyperplane.
Yes.
This is any point in epigraph. So where is the doubt? Satisfy yourself. I'm in no hurry to go anywhere.
Yeah, so we can take A transpose by B and 6 minus.
Okay, so choose.
Choose S equal to 0.
I can choose whatever I want, right? As long as s is greater than 0. So let's say choose s equal to 0. Well, let's write it down. Then we'll see. B is non-zero. That much I know. So I can divide. So let's say A transpose x minus z divided by B plus f of x minus s is less than or equal to f of z. Right? So if I want to get rid of this, what's the easiest thing I can do?
Take S.
So now I can choose s equal to 0 to get what? A transpose by B x minus. F of x less than or equal to z. Can I define this as g of z? Can I? So this is f of x, but by affine the book is this also is allowed. Strictly it should be of this type, but adding a convex function to the book is okay. So that's what affine means really. Now what is the property of g of x and f of x? I know that g of z is less than or equal to f of z for all z. But z equal to x, what is happening?
Z equal to X. So it becomes equal.
Which is what that I'm producing to you a particular g, which has this property, is affine, and at x actually ends up achieving. It's all manufactured. You tell me x, so you tell me f of x, and I will do this for you. And for each x, you'll get a different answer. Because of this form already you can see. I'm not giving you a uniform answer because that doesn't exist. When you're saying fix an x, you can write in a minute. So fix an x, what kind of function is this? A by b x minus z plus f of x. Can you draw? So let's just try to draw. Take whatever value. A transpose by b x minus z plus f of x. Right? So this was my point, let's say. How is it approaching? We know that this function approaches f of x exactly. So can you draw f of z for me? Sorry, this is what I called g of z for a fixed x, right? And I know that g of x is equal to f of x. That much I know. Can you draw it for me? That will make it pictorially clear what is going on. What is it doing? F of x is f of x. What is this? Is the question.
Just be the line that's floating in curve.
No, but there is an f of x also sitting there. That's all of it is g of z for me.
The g of x is equal to f of x. So then
Yes.
you want to just
So Friesen x as a function of z, what does it look like? At z equal to x, we know it is equal. What does it look like out other than z equal to x is the question. As it approaches x, what's happening to it?
approaching f of x functions are equal.
Because at x equal to z, the first term just disappears. So what is the first term before and after?
First time is just like a line. Where you don't like in that.
It's an x. There's nothing to do line about. Line is with respect to z now.
Like
Yeah. So it is somehow coming and hitting x. And now what happens after that?
so after x.
Before x, after x, what? Like, just to make it complete. So as a function of z, what does it look like? Friesen x. See the two parts which are frozen. A transpose b by x plus f of x. That much is frozen. It's only the z which has this negative slope. A transpose b times z. That's all is changing. So I just want you to visualize what is going on. Make sure that it always stays below f of z for all z. That's the interesting part. So that much we have proven. So what can it only be? Just give me a guess first. It cannot cross it, right? Anytime. So what can it do really? There is no other way. It has to follow two properties. F of z, sorry, g of z is less than equal to f of z. So it has to be on the below it. And now at that point is touching it. What else do you have? So for each point, I need a different, that's all is going on. So the separating hyperplane is giving you for each function what exactly is going on. That's all. Okay. So let's move on. Just going to belabor this point a little bit. Point points maximum. We've seen that if you take the max of f1x from f2x, and if f1 and f2 are convex, say g of x. So is g. Its counterpart, a little change. Let f of xy be convex in x. What does it mean? That if there is a y, f of x comma y is convex in x. So for each fixed y, this doesn't mean jointly. Then define a new function g of x to be supremum of f of x comma y. Y belongs to some domain A. Okay. Now, what kind of function is G? And compare it with that. This is not the same object as this. Here, what was given? For each x, I was picking out the max of the two. Here, there is some dimensionality going on. What am I given? That is function as a function of x for a fixed y is convex. And now I'm looking at the second coordinate and taking the supremum. So freeze an x, there are lots of these agents. So if this is discrete, which will be a complicated case of x1, f of x, y2, and so on. I'm freezing x, just picking the max over these yi's. That's what is going on. What kind of set is this? It's not very different from that. It's not exactly that. That's all. So whatever you try to say there possibly is also true here. So given that f of x comma y is convex in x for a fixed y, what does it tell you about the epigraph of something? So for a fixed y, what is the epigraph of f of x have a property? It's convex. So what is the epigraph of g?
Intersection of all these.
So if each of them is convex,
That is
the intersection is also convex. So this function is also convex. So just slight variation to what we've written there. So as long as you're taking the supremum over the coordinate over which function is not convex, you're still fine. That's what I was telling you. So x need not be x. X itself could be a vector. All I'm asking for is for a fixed y, the function should be convex over x. This need not be two-dimensional. Be very clear about it. X itself could be multidimensional. There is nothing stopping you from taking x to be multidimensional. Nothing stopping you from taking y to be multidimensional. All we're saying is, if free the y, then f is convex over x. That's all we're asking. Then if I supremize over all possible y's, the function remains g, function g remains convex. So this is an important property you should take away for your life. That is generally easy to remember. This is not that easy to remember. But this is also true. Just by intersection of the epigraphs. G is also convex and proof is P of G is the intersection of Y. P of X for a frozen Y. P of F dot. That's it. But once you notice this, the proof is over. Is it clear? Now we look at what happens to inf. Is it possible that we can say something interesting about if we take the infimum over this? What do you think is going to happen before I go and do something?
the infimum will be the minus of the supremum of the minus.
So what do you think will happen? You suddenly make it concave.
Minus f is concave, minus f is concave.
Correct.
But then supremum of minus f, like concave will be the one here.
Okay. So suppose so before I go to inf, if I have this, can you give me an example where suddenly you can say some interesting function is convex. Supremum over a half convex, like let's put it this way. It's only convex over X, not over Y. Simplest, we actually did this. Simplest example where it can use this is, let's say, f of capital X. X is a matrix. Lambda max of X. Now this can be written as supremum over Y transpose X Y. We've done it before. So why can I use this? I want to use that to claim that this function is convex. Why can I use it? As a function of X, what is this? Y transpose XY. What kind of function is this? Linear in X. And what does linear in X mean? It's convex. It's a convex function. I'm taking a supremum. I can apply that. And this tells me that this is a convex function. So maximum eigenvalue of a matrix is an you have to make sure that X is symmetric, is actually convex. Similarly, you can say this maximum distance to a set, which is a weird quantity. Typically look at the minimum distance to a set. So what's the maximum distance to a set? Suppose you have a set S. Minimum distance is for a point from here to here. What is the maximum distance to the set? Possibly here. Let's say X. This is d max of X comma S. What kind of function is d max of X comma S? Express it. You don't think, what is d max? How can you write d max of X comma S?
Maximum of all X, Y, and maximum of dx.
Sorry. Is supremum of all Y, X minus Y. Y belongs to S. What can you tell me now about this function d max of X comma S?
Again, like it is convex X minus Y convex.
Yeah, because it's just again linear. There's nothing stopping it from being, and then you supremize them over all possible Y. Y being convex is required. Sorry, S being convex is required. Think about it. Now, this function is not an obviously convex function. But once you have the theorem, this just directly follows. We are typically always interested in d min. What kind of function is that? Do you know? Not projection, it's a distance. Projection is the point. Distance is actually the point from X to the projection of X. So those two are different objects. You might have proven something in your homework number 1 about the projection. What was the question? Yeah, so what kind of function do you think is the d min?
Because S is convex, right?
This is convex.
So then like we can construct the supported plane, hyperplane and hyper.
Yes,
And so this will be the perpendicular distance to that hyper.
yes.
So then
Yeah, whatever you said is correct. But why does it imply anything about demon? Anybody wants to guess and give me an intuition why your guess is at least has any justification behind it? Object is clear? What does it mean to be convex? Let's go back to the first principles.
the linear combination of input points.
Right. So just think about what is going to happen. Obvious thing would be to use triangle inequality. What else would you like to do? Take an x, take an y. Look at the distance between x and the projection, y and the projection. Now look at lambda x plus lambda y. Where does the projection go?
I take the distance between x and its projection.
Yeah. So that's the, what do you mean by, let's do it again. Your point x, it goes here. Your point y, it goes here. So this is your d min of x comma s. This is d min of y comma s. Look at this line and look at its, go somewhere here. Okay. Let's call this lambda x plus 1 minus lambda y. Now let's call this d min of lambda. Let's call this point theta comma s. So what inequality has to be true for this function to be convex?
D min of x lambda times d min of x comma s plus 1 minus lambda times d min of y comma s is greater than or equal to d min of delta.
Right. But now what can you, from this picture, what can you deduce? So the middle length should be smaller than the lambda times the first length times 1 minus lambda times the second length, which appears to be visually correct. No? Whatever angle you try to draw, either one of them is going to be larger compared to the middle. That much is clear? And that will take care of it essentially. If you draw like, let's say line perpendicular, then almost all distances are the same. If you draw like this, the first point might become very close, but then the farthest point will be far enough, which will compensate for it. So what's your guess? It's not, I'm not proving anything right now. This is not a proof. But what's the guess? Is it convex or concave? If I were to guess, I would guess it as convex. I don't know about you.
In the max function, how do we compute the max function?
How? We didn't say that. There's no complexity involved here. There's no complexity involved yet here. How you do it is not a problem I'm trying to tackle right now.
For example, in this we can do it because of the hyperplane.
No. So I'm not trying to find the max. This by definition, this is max. All I'm trying to say, this is convex or not convex. That's all. What is your question?
No, I was asking that like the characterization of the minimum distance. So the distance to the hyperplane.
I don't know. Yeah. That need not be something nice. And this is also an object which generally doesn't appear, but it's good to know that something like this is true. Because you never know, you'll come up with a problem where max is useful. But this is like a bread and butter object, minimum distance to a convex set. Okay, so if I were to want to prove this convex, what do I have to do? I have to somehow prove something like this. That what function can I write this distance as? Sorry. If I wanted to write this, I would write it as inf of x minus y. Y belongs to S, right? Okay. So inf is involved rather than the max. So let's do slightly more general. Let's say, let F be now jointly convex. Okay. I didn't need this when I was looking at soup. And S be non-empty convex set. Then f of xy inf over y is this exactly fits our bill. What we wanted to prove is a special case of this. Projection is over a convex set and minimum distance is nothing but f to be equal to norm of x minus y. Okay, how do I prove this? This is very special, okay? Something like this doesn't hold in general. So what is first principles? You don't have to come up with any new idea really. So if I want to show that g of x is convex, what do I need to do? G of lambda x plus 1 minus lambda y is less than or equal to something. What is g of lambda x plus 1 minus lambda y? Where can you start? Just by the pure definition of it. So by pure definition, what is g of lambda x plus 1 minus lambda y? This is equal to inf over y. Okay, sorry. I shouldn't use y here. Let me use something else. Let me use x1, x2 is equal to inf over y f of lambda x1 minus lambda x2. Okay. This is pure definition. Now, given that this is inf,
less than or equal to 1.
so what should which y should I pick? There is an obvious y I should pick. This is true for all y, right? So then it's less than or equal to for any particular choice of y. What is that particular choice of y?
We can use any value.
Oh, let me proceed with you and we'll see the problem. No? So let me just use lambda y1 plus 1 minus lambda y2 for some y1, y2. This is also new quantity because it's convex. See, this is convexity in play. That S is convex. So this is just one such one. So far I've not done anything. Now what can I do? I know that f of x, y is jointly convex.
Then lambda
So this comes out now. Now what?
This is true for any y1, any value.
But this is not.
Yeah, but the y over there is not.
So some more. But what special choice of y1, y2 I could have made? This is true for any y1, y2. By the definition of inf, what special y1, y2 I could have picked? So that I can transform this as a function of g. See, end goal here is to write it as function of g, not as f. So pick special y1, y2s so that I can write in terms of x1, x2s, g of x1, x2s. What is g of x1? Is infimum of x1 comma y. So what kind of y's exist if I wanted? I'm optimizing over all possible y's. Something very close to optimal. What is the optimal value? G of x1. For a fixed y. So if I wanted to come close to g of x1, can I make a choice of y1 and come close to g of x1? Tell me, if there exists a y1 such that f of x1 comma y1 is less than or equal to g of x1 when it epsilon 1. Fix an epsilon greater than 0. Does there exist such a y1?
Yeah, but the definition of infimum.
What is g of x1? Infimum over all possible f of x1 comma y. So close enough. What can I get? I can get such y1s. Similarly, I can get y2 such that f of x2 comma y2 less than g of x1 plus epsilon. So I'm fixing an epsilon, essentially close to 0 is what I'm going to pick. So what does it mean? Right. So right here, make this choice. Such a y1 and y2 exist. Just make those choices. And lambda y1 plus 1 minus lambda y2, because of the convexity of S, also belong to S. So all of this is fine. So this is equal to what? Lambda times g of x1.
That's 1 minus lambda times g of x2.
Something is missing.
Plus 2
What else? Plus
2
epsilon times lambda plus 1 minus lambda. So it's okay. So what have I got? This is less than equal to this plus epsilon for all epsilon greater than 0. What does it mean?
And then it must be less than or equal to lambda.
Yep.
I think less than or equal to lambda g of x1 plus 1 minus lambda.
Why?
It's true for all epsilon.
Strictly greater than 0. So you have to make some argument, right?
So like that set will be the intercepting epsilon to be equal to 1 by m. Intersection of all 1 by m.
Yes.
So that intersection of all that plus 1 by m will be the closed set.
So we'll have to some machinery, no, I would say machinery, some trick. Okay, let's not even call it a trick. Some argument is missing here. What is that argument missing? What have I shown? That the function is convex up to this additive factor of epsilon for all epsilon greater. So I could choose whatever epsilon I want. So what should I do? I want to claim that this actually implies that the function g is in fact convex. Have you ever seen inequalities of this type? F of x less than or equal to f of y plus epsilon for all epsilon greater than 0. What do you conclude? No more convexity is involved now. All we are trying to say is the following. Let f of x be less than or equal to g of x plus epsilon for all epsilon greater than 0. What can you conclude from this? So if you have not seen this, either see it or do it yourself. Okay, that's all is missing. What have we done so far? Gets you till here. Intuition will suggest that, yeah, I should be able to do epsilon. Essentially limiting argument. That's all there is. You can do contradiction if you want, or you can do a constructive proof. It's up to you what you like. But this is what the final nail is. We have come so far, you need to go here. If you're not seen, useful exercise to do this. How else I could have done this without going through all this trouble? Can you give me an epigraph based argument? It won't be an intersection of epigraphs because it's an inf. Having trouble following something? Everything is fine. So now think of what can I write the epigraph of g of x as? It's brutal. There's nothing really to think about. Just write the set epigraph of g. Write it and tell me what it is. Automatically f will get involved, and that will give you the tell what exactly is going to happen. Okay, let me give you a hint. So let's take a set which is convex. If you take a projection of it in some sub-dimensions, everybody understands that, what it means. Take a convex set, take its projection. So think of a convex set in 2 dimensions. Take its projection in 1 dimension. If the set to begin with was convex, will its projection remain convex? That's your hint. So epigraph of G can be written as some projection of some convex. You're not writing brutally. Write brutally the definition of epigraph of G. There is nothing really going on.
X comma t is that p is greater than.
Right. But now there is G is defined in terms of F. So if you go one more step,
If you know that p is greater than equal to f of x comma y for all that.
okay. So what does it look like in terms of the epigraph of F?
It's greater than t.
You have a free variable, which is Y. You're optimizing over Y. So what is epi of G is x comma t such that t is greater than equal to G of x. Right? How else can I write this? That's the trick. So x is here, dash is here, and t is here. Okay. So I'm adding one extra component to what? And remember, g of x is inf over y belongs to s f of x comma y.
Y comma t is that it belongs to the epigraph of x.
For some so supposing this is true, I don't think everybody is here. Supposing this is true, why is epi of G convex? Epi of F is convex because it's convex in both x and y. So what am I doing from here to here? I'm just dropping one dimension. So it's nothing but a projection onto a lower dimension. This is convex, so this better be convex. Now, why is this true? This is by definition. What is t greater than equal to g of x? G of x itself is inf over f of x comma y. So just plant it there. There's nothing really going on. So just this belongs to epi of f for some y. What is epi of f? F is a two-dimensional function. Just write epi of f. It will clear up everything. Is x y comma t such that just using that. There's nothing else going on. If you plant g of x, open it up, nothing but infimum. So it's just for some particular y, this is true. And then you're just collapsing one dimension. So individually, so that's what I said. Brutally write the definition of epigraph of G. There is nothing where it can go wrong. So first write epigraph of F, first write epigraph of G, try to write them in each other. This is nothing but a projection of epigraph of F onto G. So by this result, what you have shown is that you don't have to do this ugly exercise, which will possibly become very nasty. We've directly shown that as long as they're jointly convex, S is convex, infimum is convex. And x minus y whole square, is it jointly convex in x comma y? Mod of x minus y better be jointly convex. Otherwise, there's nothing which we can do. That we'll have to check. Nothing much is left to check, but whenever you're applying the full force of such a powerful theorem, you have to check every single condition. Clearly, S is convex, that you don't have to check. But it needs to be jointly convex in x comma y. All right. Done. Let me define two derivatives of convex functions. We'll do some other properties. So strict convexity, everybody remembers, right? The inequality is tight, or inequality, sorry. So what was our convexity? F of lambda x1 plus 1 minus lambda x2 should be less than equal to how much? Lambda x1 plus 1 minus lambda x2. Always the picture helps. So what is this point? And what is this point? So this is my f of this, and this is lambda of f plus 1 minus lambda. There's something called quasi-convex. Things are not always convex. So a function Rn to R is called quasi-convex. It's like not, doesn't satisfy all the properties for a convex set, but comes close. If its domain is convex, see, we needed this even to define a convex function. The domain should be convex, and all its sub-level sets. What are those? Somebody remember? What are sub-level, alpha sub-level set for a function? X belongs to domain of f, where f of x is equal to alpha. And all its sub-level sets are convex. That's my definition of a quasi-convex. So not asking for the definition above. So give me obvious thing, a quasi-convex function which is not convex. So every convex function is quasi-convex, that much is clear. Give me a quasi-convex function which is not convex. Okay. Why does it satisfy? Don't worry about domain.
So f of x less than or equal to alpha would just be like x is less than or equal to alpha to the power of 1.
So example, x to the power 3 or 1 by 3? What does it look like? It's like this. Oh, it should be this way. It's increase. Definitely is increasing. It can't be this.
It's like, yeah, like that.
Just give me here.
Okay, like that.
Okay. Let me draw x square. Okay. Now in comparison to this is this way, or it is this way.
This is fine.
This is x square.
Yeah, x cube is like-
It's much faster. Oh. Fine. So this is x square. This is x cube. And this will be inverted this way. Okay. Fine. Now, why is it not convex but quasi-convex?
So it's not convex, like really, I mean, we take the.
We have a quick test, right? What goes wrong? The second derivative is
The secondary.
not necessarily positive everywhere. Okay. But why is it quasi-convex?
So like, let's take an alpha.
Hmm.
Okay, so then f of x less than or equal to alpha would just mean that alpha is
Okay.
x is less than or equal to 1.
So-
alpha to the power 1, right?
All of this will essentially be the set, and it is convex. So it's quasi-convex. Any other example? A function which is not even quasi-convex. A function that is also not quasi-convex. What about log? Is it quasi-convex? What is the log function? Just simply this. Is it quasi-convex?
But then x would be again less than or equal to alpha. So
So whatever level you draw.
then x is less than e to the power of alpha.
Mhm.
All the except that x is less than e power.
Okay.
So then. That would be.
Okay, so give me a function which is not quasi-convex. See, what all is ruling out is functions of this type. That's all it's ruling out really. It's demanding very little. Convex function needed one u, and that's all you got. Here you can do as many times as you want. That's not allowed. That's all it's saying. You still have only one dip. This is very, very loose. That's all it's saying really. You can't have these alpha level subsets, alpha sub-level sets, a discontiguous sets. They're not allowed. That's what it's really saying. Any other function which is quasi-convex but not convex? Step function is quasi-convex.
Yes.
Yes, it was not convex. Anything else? Suddenly the whole world opens up from convex to quasi-convex. Anything else?
Again, so it's like. He two straight lines, then again.
Yeah. This is hardly convex, right? But quasi-convex? Because once it crosses a level, whatever remains below is kind of, I don't know how to say it. Yeah. This is here. We draw it here. All of this gets. So it's a very very little demanding in some sense. The definition is very little demanding, and we'll say something interesting. So that's quasi-convex. Now comes something which is stronger than convex. So that is weaker than convex. This is strongly convex. So what is our characterization of a convex function in terms of its first derivative? So we said something is f of y is greater than f of x plus derivative of f of x transpose y minus x. It's true for all convex functions. Right? Remember this, right? Always, please remember this. This is an alternate characterization of a convex function. What it really meant, when you draw this, this is your y, this much is y minus x, and that's your gradient at x. That f of y is above this. Convex function is, or this first order Taylor series, an underestimate of what the true function is. I'm going to add something to this. So I'm going to strengthen this inequality. So function, a convex function, let's use it, is called mu strongly convex if f of y is as it is, no change, plus gradient of f of x times y minus x plus, this is the new extra term, which is positive. So I'm pushing it even further away. It has to occur even fast. See, the convex function, even a linear function is convex, or a constant function is convex. This will not allow all that. Mu by 2, and mu is greater than 0, okay? Y minus x. So this is the additive extra term needed for it to be strongly convex. So can you think of a function which is strongly convex? One strongly convex, for example. When you think of convex function, what is the first function that comes to mind? Is it x square strongly convex with mu equal to 1? Don't do it. It will be laborious. If you see it, you see it. Otherwise, we'll try to give an alternate characterization where it will be almost trivial. How much have I added essentially? That's what you see. Compared to a convex function, what have I done really?
I think the same, the Taylor approximation.
There's no gradient, nothing. Half times y minus x simply, the whole square. And mu is the parameter. How much we're increasing, that much I will say it's that much strongly convex. If mu is 0, I go back to the convex function. So alternatively, I want to say the function is strongly convex if and only if define a new function f of x minus mu by 2 mod x square is convex. Now is x square strongly convex? Is it obvious? It will simply give you mu by 2 mod x square. And that clearly is convex. So x square is at least one strongly convex. Okay, who wants to prove this? It's actually a straightforward exercise. Remember the definition. Definition is this. It's if and only if this particular function is convex. So when we have convexity, what is the first thing I wrote? For a convex function, f of y is greater than f of x plus del fx transpose y minus x. Let's take this to be convex and try to see if we get back our inequality. So what is it? F of y minus mu by 2 y square greater than f of x minus mu by 2. What is the gradient of this? Gradient of f of x. The mixing of a lot of x's and g's. If it's not clear, ask me. This is the characterization. This is true if function is convex. So I'm applying this g function to this and opening it up simultaneously. So this is f of y minus mu by 2 y square. This is g of x as it is plus the gradient of g. What is the gradient of g? Gradient of f minus mu by 2 times 2x transpose. And what is y minus x? As it is. Okay. So what can I do? I can keep f of y here greater than f of x here minus mu by 2 mod x square plus mu by 2, sorry, not here, y square. That much I'm done. Now I have to only worry about this plus y minus x and minus mu times x transpose y minus x. So what is x transpose y? See, essentially I want to claim this is x minus y whole square. That's what I want, or y minus x. There's the same thing, right? So there is a mu by 2 already there, which is good news. This is not good news, or this is not good news. What do I want? I want a plus y minus x square. So y square should be a positive sign, x square should be a positive sign, and a minus 2yx should come on. So what is, this is correct. This is not sufficient. But what do I have here? X transpose x with a positive sign. So this is equal to f of x. Take the gradient over here plus the gradient f of x times y minus x as it is. I can keep this guy here, mu by 2 y square as it is, plus mu by 2 x square and 2 times 2 by 2 times mu x transpose. And this is nothing but plus mu by 2 x, or rather y minus x. That's all. So if you like this, you can say this is my definition of convex, strongly convex. If this function is convex, then I am mu strongly convex. Generally, the starting point mostly is this. It's easier to actually think about it also. That what am I doing? To that underestimate, I'm adding an extra term which will push me away from it. That's all. So this is what is called strongly convex. So there is no strongly convex. This is it. This is convex, strictly convex, quasi-convex, strongly convex. This is the strongest requirement. Convex is reasonable. Quasi-convex is very liberal. Strict convexity gives you only a little bit extra than convexity. But strong convexity gives you a lot. And we will see what that lot is over a period of next few months. But at least keep in mind, the book surprisingly doesn't talk much about strongly convex function. But there are other books which do a lot, like they worry a lot about strongly convex function. This particular book doesn't seem to pay enough attention to that. But it's very important. It has a very nice interpretation this way or this way. You can try to interpret for yourself. What does it mean? This function being convex, what does it mean intuitively? Can it go slower than x square? Let's just put it that way. Can a strongly convex function go slower than a quadratic function?